Chapter 12, slides 16 to 22. Okay, so we're still on the discussion of how to make alcohols. Again, how to end up with an alcohol as a functional group in my product. Okay, one of the most widely used methods. I mean, when I see an alcohol on a molecule and I think, how could I make that molecule? This is the method I think of first. And it's probably one of the most widely used. I'd say, making new carbon-carbon bonds like we did in the last set of slides is also related to this and also widely used, but reductions are probably the most common. So I want to take a step back first and look at the word reduction. Okay, you'll see it on these slides, and what it's showing is that when you move in the direction of a carbonyl, like an aldehyde, and you reduce an aldehyde, you end up getting an alcohol. Now, you guys have spent lots of time talking about oxidation reduction chemistry, right? And in general chemistry, you guys were very hung up on, you have to look at the metal, and you have to look at the oxidation state of the metal, and is it going from +3 to +2? Did it, Leo says GER, did it lose electrons, gain electrons, in order to figure out oxidation versus reduction? Well, what is true is that oxidation in one direction, as you can see from my arrows, if you do the reverse, is the reduction. Okay, so the opposite of oxidation is reduction. Now, how we define it in organic chemistry, since we're not really dealing with metals per se, although we are, they're going to be more in line with the reagents, but we're not always going to use metals. And so how do I understand whether or not a molecule like ethanol is being oxidized or reduced? So here is a very loose way of defining oxidation and reduction to an organic chemist. Okay, and there are expansions to this, but let's just think of it this way. Oxidation for now is going to mean when a carbon reduces the number of CH bonds, right? So you reduce the number of CHs you have, and you increase the number of CO bonds. Okay, so if you look at oxidation, let's look at the top. You have got a carbon with 2 hydrogens and 1 oxygen bond, right? So 2 H's and 1 oxygen. If I convert the alcohol into the aldehyde, that same carbon has now 1 H off of it and 2 oxygen bonds, right? The sigma and the pi. And then if I oxidize the aldehyde up to the carboxylic acid, I now don't have any hydrogens off of the carbon, and I have 3 oxygen bonds off of that carbon. So you can see that going from the alcohol to the aldehyde is an oxidation, and going from the aldehyde to the carboxylic acid is an oxidation. In reverse, I'm doing reduction. So reduction is the opposite. Reduction is increasing the number of CH bonds and decreasing or reducing the number of CO bonds. So if I started with the carboxylic acid with 3 oxygen bonds, I reduce it to the aldehyde. Now I have 1 more CH bond and fewer CO bonds, and then reduce it all the way to the alcohol where I have 1 CO bond and 2 CH bonds. So you can see this process of oxidation in one direction, reduction in the other. In this set of slides, we're going to focus on reduction. Why? Well, because if you notice that the products of reduction end at the alcohol, and alcohols as the products is where we're at in this chapter. So reduction, we need to increase the number of carbon-hydrogen bonds. Well, how do we do that? We need to make hydrogen the nucleophile. You've seen hydrogen as an H- before. Remember NaH. Now there's reasons why we don't use NaH for this reaction, but I just want to point out that you have seen the H- before. H- is H with a lone pair. This is called a hydride. And that hydrogen, because it has a lone pair, is negatively charged, as opposed to H+, which doesn't have any electrons and is called a proton, because that's all it is one proton in its nucleus, and it doesn't have any electrons in it. So a hydride is the opposite of H+. Now hydrides, I'm just going to show you the mechanism, and then we're going to go back and talk about the reagents that you can purchase to use to utilize an H- hydride. So let's assume I have an H-. I could start with an aldehyde. Let's say I started with this propanal, and I introduced an H-. Well, it's a strong nucleophile, not very stable, right? H- is definitely not stable. Talk about carbon minus being strong. H- is very strong. It's looking for something to react with. So we have our strong nucleophile, H-, and we have our electrophilic carbon source. So you're going to see the same 1,2 addition mechanism that we saw in the previous slides. The H- goes in and up. And guess what? We're going to do the same exact evaluation that we did with the other in up. This time we've added this new hydrogen. So we've increased the number of hydrogen bonds. We've decreased the number of carbon-oxygen bonds. We still should do the same evaluation of whether or not these electrons on the oxygen, right, because we've just formed our tetrahedral intermediate, and we have to evaluate whether or not that can come down. Can the electrons come down? Well, I have a carbon, hydrogen, hydrogen. Remember, only things other than carbon and hydrogen can get kicked off. I'm stuck. The only thing left to do is work it up. So I work it up. And I end with the alcohol as the product. I went from the aldehyde to the alcohol. Okay, so how do we get H-? Well, we can purchase reagents like sodium borohydride or lithium aluminum hydride or lithium borohydride. Of these reagents, the hydrides are the most reactive when their counter ion is lithium. So the lithium aluminum hydride and the lithium borohydride are more reactive. Why? Because lithium is more electropositive. If the lithium's more electropositive, it empowers the hydrogen to be more negative. Okay, so the more electropositive the counter ion, the more negative the hydride. There's other reasons for this as well, to do with the counter ion and its association to the oxygen. This also helps the reaction along. Think of it. The lithium is more electropositive, so it's more attracted to the oxygen of the aldehyde. So if there's an attraction with the lithium and the lithium carries the reagent, right? Because this is a salt. If the lithium, which carries the hydride with it, is more attracted to the oxygen, then it's getting things closer together for the reaction to occur. You're getting things closer so the BH4 can deliver its hydride. So I want to talk a little bit about these reagents. I'm going to use the next slide to do that. I want you to think about all of these boron and aluminum agents, right? So sodium borohydride. Let's just draw this out. Remember boron and aluminum. They're in group 3. They have 3 valence electrons. This means that in their normal bond trend, they have 3 bonds. They make 3 covalent bonds. Okay, so that's their normal bond trend. They're sp2 hybridized. They have 3 single bonds, so they're trigonal planar, but they can't help themselves. They're electropositive enough that they can encourage another bond, but whoever comes to make the 4th bond with them has to bring both electrons to the table. So if you look at boron and aluminum, they both have 6 electrons around them, and it doesn't stop them from wanting 8, right? But they don't have anything to give to make the octet. So if you think about it, a boron with 4 covalent bonds around it, if you actually calculate the formal charge, it has a formal negative charge. Okay, that's why its counter ion is sodium. So together, this is an ionic salt. Once you take that ionic salt, so it's a solid salt you can purchase in a bottle. Once you take that salt and you dissolve it in a solution, it dissociates, and the boron is like, I don't want to be negative. So what it does is it wants to pop off one of these hydrogens as an H- to get back to its normal BH3, 3 bonds, and back to neutrality. So in solution, it sort of expels one of these extra bonds, but take your electrons with you, so that's how you generate your H-, the counter ion being sodium. Same goes for, I don't know, let's try it with aluminum. Lithium aluminum hydride, same thing. The aluminum with 4 bonds gives an overall formal charge of negative, the counter ion being lithium. Okay, and so once you put that salt, that ionic salt in solution, it pops off one of these guys, giving you an H- hydride. Okay, so that's why you see the reagents you do. Okay, you can see the extra valency of the octet valency of these borons and aluminums, and that's where you're getting the extra H- from. So let's take a ketone. I'll do cyclopentanone. Let's say I reacted it with sodium borohydride. Okay, one of the common reagents. You can shorthand it and say, well, this is just an H- source, so I'm just going to concentrate it as H-. I see my carbonyl carbon is the electropositive carbon, and the hydrogen is going to take its 2 electrons and attack in an in-up fashion. I then evaluate the atoms around the electrophile. I have carbon, carbon, and hydrogen. None of them are good leaving groups. So I'm stuck. There's nothing left to do but to work up under acidic conditions. To protonate my oxygen, giving me cyclopentanol. Okay? Let's try another one. This time we're going to use, let's try this ester, and I'll react it with lithium aluminum hydride. Remembering that that is a hydride source, I can shorthand it, identify my electropositive carbon, and do my in-up chemistry. In, up. O minus, just added a hydrogen. So one of the things I want you to notice is that when we were attacking a carbonyl with a carbon, I just want to point this out to you. Say methyl lithium. When you're adding something like a carbon to a carbonyl, notice the arrows that I've been using. Remember the point I'm making. When you have nothing but a carbon or hydrogen, those are not good leaving groups, so they can't come off. This means that when the electrons, if the electrons can come back down, the thing you just put on, the hydrogen or the carbon, is not going to pop back off and go back to the starting material. So notice that for these reductions and these Grignard type reactions that I've been showing you, the arrows have been unidirectional toward a product. We're going to keep moving that train in a direction because the bonds I keep putting on are not reversible. They can't be taken off. Okay? So we're going to come back to this point in future chapters, but I just want to point that out to you. Adding an H or adding a carbon to your carbonyl is non-reversible. Once you put it on, it's stuck there. Okay, so this was just an aside. So the H minus went in, we went up, so this is my in up. I have to evaluate. I've got carbon, hydrogen. I've got something other than carbon or hydrogen. So I'm going to come down and out. So I've done a down out. There's my down out. Now, aldehydes are reactive with lithium aluminum hydride, right? That was the first reaction we did. We did an aldehyde with an H minus. We've done a ketone with an H minus. Now we're doing an ester with an H minus, but esters have something that can pop off. So we had to do a substitution. In up followed by down out. But aldehydes are susceptible to H minus. In and up. Now evaluate. We have carbon, hydrogen, hydrogen. Nothing now can pop off. So I'm stuck. So I work it up. And I end up with this alcohol as my product. Wonderful. Okay, so reductions are a way for us to go back. You could start with a ketone and end with your alcohol. You could start with an aldehyde and end with your alcohol. I didn't show this to you, but you can start with a carboxylic acid, which is very similar to an ester, and you have to go twice through, because after you make the aldehyde in the down out, it does a further reduction to get all the way to the alcohol. So you guys now understand how to go from a carbonyl all the way down to the alcohol. At this point, I think it's very important to start looking at different carbonyl electrophiles and their reactivities. So all electrophiles of a carbonyl are not equal. What does that mean? Well, if I look at a bunch of carbonyls, right? I've got an amide here. I've got an ester. I have the carboxylic acid. I have a ketone. I have an aldehyde. And I have an acid halide. These are all different carbonyl types, and they're not all equally reactive. Some of them are more reactive than others. So let's rank them, okay? What I need you to do is I need you to think about what differs about them, okay? So if you look, you can see that I drew them all with one methyl group, okay? They each have a methyl group. So the methyl group is the same across all of them. So what's different is having a halogen, a hydrogen, a carbon, an oxygen, and a nitrogen. That's what you have to look at. Everything else about the carbonyl is the same. So let's go back to our inductive effects. A halogen, like chlorine, is considered to be an electron withdrawing group. So if you're withdrawing electron density, you're making the carbon it's attached to more electrophilic. A hydrogen is neither electron donating nor withdrawing, and it has no steric hindrance. So aldehydes are actually pretty electropositive. Here's the divide. A ketone, like a CH3, adding another alkyl group there, you're adding a little bit more steric hindrance because you've got this tetrahedral ball there, and technically electron donating. It's weak electron donating by induction, but it is electron donating. So now what you're doing is you're making the electropositivity of the carbon less, because you're now donating electron density towards that electropositive carbon. So you're shrinking the positive nature of that carbonyl. Now all of these I would say are about the same. The ester and the carboxylic acid have about the same reactivity. And you can think of this as the fact that oxygen is an electron donating group. And because it actually has lone pair electrons that can, by resonance, donate in, right? You've got electron donating. So this diminishes the electrophilicity of those carbonyl carbons. And nitrogen is a really, really, really good electron donating group. Think of it this way. Oxygen is more electronegative, greedier. It's greedier than nitrogen. So that means if nitrogen is not as greedy, it's more generous with its lone pair. So it's a better electron donator because it is less electronegative, less greedy. And so what that does is it just really diminishes the electropositivity of the carbonyl. So amides are the least reactive out of all the carbonyls, which, thank God, right? I mean, think about proteins. Right? You have a peptide bond. Right? That's a peptide bond. Right? So peptide bonds right here. It's just the amide bond, right? So you have these long chains of amide bonds. Think about it. If amide bonds were super, super, super reactive, they'd be reacting all the time. Nucleophiles would be attacking them, going in, up, down, and kicking them off left and right. You'd have them breaking willy-nilly all over the place. But thankfully, amides, or the peptide bond, is strong. And it diminishes the electrophilicity of the carbonyl it's attached to, making it not as good of a site to be attacked. This is a good thing for us to be stable, right? So given this trend and knowing which hydride is more nucleophilic, we can understand the following statement. Lithium aluminum hydride and lithium borohydride, okay, because they're more reactive, if you want to reduce these lower end, lower reactivity carbonyls, because these two are the more higher reactive ones, these are what you use to reduce carboxylic acids, esters, and amides. Okay, sodium borohydride isn't quite going to cut it with the lower end, lower reactivity ones. So therefore, lithium aluminum hydride, lithium borohydride, they reduce all of them. But sodium borohydride, the weaker one, we use these for aldehydes and ketones. Acid chlorides is fine too. So there's sort of a line here. You can kind of see it as the higher reactive ones and the lower reactive ones. And we're going to be using this schematic of reactivity for carbonyls in subsequent chapters. Okay, this is just the beginning of our carbonyl discussions. One molecule that you guys probably have a little bit of experience seeing is NADH, right? This is nature's redox tool. As a chemist, my redox tool is sodium borohydride and lithium aluminum hydride and lithium borohydride. But our bodies have very, very complex and beautiful ways of using H minuses, because it doesn't clearly have a metal like we think of, right, in these other ones with aluminum and boron. So NADH, notice that the H of NADH is the hydride. So if you're ever like studying biochemistry and you can't remember NAD plus and NADH, just remember that NADH is your hydride. It's the reducer. It's your reducing agent because it is the provider of your H minus. Where does nature get its H minus from? Well, this whole big massive molecule here is NADH. And in green, you'll see there's a sugar, there's a base, adenine, and then you have a diphosphate linkage here, and then you have another sugar, but none of that in green is part of the reaction. Okay, the reactive center of NADH is far to the right in orange. So the reactive site acts as our H minus delivery system. Okay, so let's reduce this molecule down. Let's just shrink it down because we don't really need to see any of this stuff because it's not playing a role in the hydride part. Let's just focus on the orange. So you can see here that that whole big green part of the molecule is just now shrunk down to just an R in green, okay? Because it really doesn't play a role. So why is an enzyme required? Well, the driving force for this mechanism, which we're going to actually discuss why this is happening, but we need to know a little bit more chemistry to fully get this process. But I'm going to show you where the H minus comes from, and I'll actually come back to the slide when I do further notes, future notes. Notice that this nitrogen, which as we know is an electron donating group, by resonance in a sense, right? This is actually a reaction, but you can see that these electrons can dump in, pushing the pi electrons to move over. Now, normally we would never do this in resonance because moving the pi electrons over requires a bond to be broken on this tetrahedral carbon. And that's in fact what happens. And you might think to yourself, wait a minute, she just told me that hydrogen is a terrible leaving group. Why would this hydrogen leave in order to accommodate that? And the answer to this is going to have to be answered in a subsequent chapter. So you're just going to have to trust me right now and take it at face value that that red hydrogen is going to get popped off as a leaving group. But the enzyme places the ketone in very close proximity, so it's not floating around as H- for long, if at all. That H- pops off and acts as your H- going to the carbonyl of the ketone in a 1,2 fashion. And then because everything is at the ready in our bodies, there's another proton source very close by to quench that O- that would form. So here you go. Here your ketone, because of the NADH molecule, that's providing the H of NADH as your hydride to reduce the ketone to the alcohol. So NADH becomes NAD+. You can see it's the nitrogen here. When it donated its electrons, it's now outside of its bond trend with 4 bonds. That's where the plus comes from, the NAD+. It's that nitrogen. Now ADP and NAD+ get together, and ADP ends up oxidizing NAD+ back to NADH, and in the process turning into ATP. So NADH feeds into the citric acid cycle, and NAD+ feeds into ADP conversion to ATP. So you can see how all of this just works, and blends synonymously with one another. So the one thing that you guys have to, I'm so sorry you're going to lose sleep over, is why this molecule wants to push out an H- as a leaving group. That, unfortunately, we're going to have to answer at another time.